All right, thanks for coming. I'm Ben Clark, the organizer of this meetup and chief architect of Wayfair. Just first, a huge thank you to Akamai for hosting this meetup. We usually host it at Wayfair, but there was a big event over there, so I sent out the SOS to friends and acquaintances, and in Akamai's case, they're also a gold sponsor of the meetup. So big thanks to them for that and for this, and to our other sponsors, of course, Instart Logic, New Relic, Soast, and Catchpoint. Tonight we have it's like a rock concert. There's a headline act, that's me. And I mean, there's an opening act, that's me, and there's a headliner who's we're really delighted to have Baron Schwartz here today from Vivid Cortex. And so I'm going to give a little talk about scaling performance monitoring at Wayfair, and then he's going to give a talk called Sampling is Hard. All right.
Which is more like a B movie than a rock act.
Yeah, well, okay. So here's the what are these then? The trailers, right? And then we'll have the movie after. All right. So scaling performance monitoring at Wayfair. So what I'm going to do is do a little introduction, talk about our stack for a minute because that helps frame the rest of it. Talk about the people that we have needed to monitor what we're doing, tools and processes, and then a couple comments on the scale. So if you don't know Wayfair, it's a home goods retailer based in Boston, public company as of last October, has 5 brands, and we're in 5 countries. There's a lot of us at Wayfair, and there's about 350 plus in the engineering group. I'm the chief architect of Wayfair. I started in 2011. I was promoted into this role a year ago. You can get in touch with me in all those places. When I started out, I looked more like that, and I guess I don't really know all that much math, but I'm kind of a testament to the fact that you can get a lot done with Bayes' theorem, a MacBook Pro, and enough coffee to kind of get you going. That was when I started. All right, so Wayfair stack, just a little background. So from 2002 inception to 2010, it was classic ASP plus SQL Server, right? Not a lot going on there in terms of stack complexity. Not a lot to monitor. We had to do some monitoring, but it's not all that interesting to talk about in retrospect. We were definitely living that sort of lean startup lifestyle where you just focus on the business problems and make do with the tools you have. Eventually we broke the seal. 2010 we added one other thing because search got slow, so we added solar. And then, whoa, my goodness, that's 2011 it pretty much started looking like this. There was a little bit of incremental add, but that's a view of major components of our stack. We have 3 data centers now in Waltham, Seattle, Washington, and Dublin, Ireland. And so this is, you can see the boxes and arrows. We love boxes and arrow diagrams, don't we? And then this lower left-hand corner is Waltham only. This is kind of the central command, so big data, Vertica, a few SQL servers that aren't duplicated throughout the environment, as some of them are. All right, so people, what do you need to run all this? So this is our network operations center the day before our IPO. If it looks suspiciously like a kind of low-rent version of Akamai's network operations center, that's no coincidence. We don't have to monitor the entire internet. We just have to monitor kind of a big store. But we still, if you want to send a couch to the moon or something like that, it's probably good to do it from a place that looks like this. Our CIO is former Akamai, and he put a lot of this stuff in place. Teams to monitor. So our infrastructure team has kind of fluctuated between, I'd say, 30 and 40% of the total engineering group. And the sub-teams that are involved in what I'm going to talk about are site reliability, infrastructure tools, there's a monitoring team, frontline production support. There's quite a few other teams within infrastructure, and these teams are not totally dedicated to what I'm going to talk about. But that's the sort of pool of people that we have to work on these things when there's a sort of a hot moment in terms of project planning, when you're standing up a new piece of infrastructure or something like that, or focusing on one of these things in a serious way. All right, so tools and processes. So why do we need to monitor? So this is a chart we have on our engineering blog of Git change sets that we push to production per day. is between 100. The short bars are the weekend, but otherwise we're pushing between 100 and 250 get change sets every day. And we definitely take the view that we'll test those as much as we can, but there's a limit to how much you can really do with that. So you're going to look at the results, and we batch these up into what are called deployed trains, and they have conductors, and the conductors have a dashboard which is in a tool called Kibana. And so when we see a lot of red there after a push, we often roll it back or fix it quickly and push forward, or do one of these things that continuous deployment shops do. The developers and everybody else has a kind of self-service alerting thing that can look at the data store that Kibana is looking at, and a couple of other data stores, so they can go in there and create things that are sort of checking, am I past a threshold on something, or is a certain type of error happening at all or happening frequently. You set those up in there, and you then get emails, and those are a little spammy. They're not very subtle. They kind of keep nagging you until you do something to make them shut up. If you need more control, there's another tool, open source tool we have called Zabbix, backed by MySQL, where you can set up dashboards with a little more subtle alerts, the kind that kind of, they send you an alert when something gets in a bad state. So you don't have that I'm tuning out the spam problem quite as bad. And then you know that you need to react to that one email, you fix it, get back, and then it sends you another email saying things are happy. This is reporting that we don't just use it for web performance. This is reporting that all of our iPads where you can book conferences in Wayfair rooms can be pinged. So that's a happy result. We have some commercial tools as well. Not a lot. It's very DIY shop Wayfair, but we do have SolarWinds for network monitoring, and this is sort of a good view of our different data centers. This is one of those sort of live interactive maps that we use to see when there's kind of, I've got a lot of green on these things because I don't want to make us look bad, but once in a while those balls turn red and we got trouble. We do synthetic testing with Catchpoint. So this is a graph telling me that the means on the category pages are for our UK site are relatively happy. And that green line there is 100% availability. We love that line. That line is awesome. We do real user monitoring. We, like a lot of people, we hack the performance timing object in the browsers. You don't get Safari, but you get enough of the others to give you a good idea. This is kind of the iconic graph of the performance monitoring industry. The classic conversion rate and speed graph that everybody. I think there's if you sort of naively think that if you can just move these bars to the left, you'll get exactly that conversion rate for everybody, you're ignoring some confounding variables. It's it's possible to get a little too excited about this graph, but it certainly contains some suggestive information, shall we say. Server-side timings, we use Graphite. So this is just one of those things where developers, again, pretty self-service. You just kind of put these things, counters of various kinds and timings in your code, and then you can mix and match all the individual counters into whatever kind of comparisons you want to see. This is just means and upper 90s of performance on a certain class of page in two different data centers. So we got some nasty spikiness going on there, and one of the data centers is looking healthier than the other. So that's probably something we need to look into. This is what we call a heads-up display. It uses the charting package HiCharts. Same type of data, but spiffier interfaces, easier to compose things that give when people do see a stream of errors or something like that, they can easily sort of go in and look at the key components in one place. We used to have Coradient as a network tap monitor of thing that would show us live traffic, but we were pretty DIY place, and so this is a picture of my colleague Dan Rowe speaking at Monitorama last year and showing the Wayfair sniffer WIF, which you can find on GitHub/Wayfair. And then you can drill down on an individual session, see this person came in from Google, surfing around on Wayfair, didn't buy anything. What's up with that? Clearly we need to intervene with this person. This is one of our graphite graphs that's hopeful. We call it the means of production. I think the person who put this together is some kind of crypto Marxist or something like that. But that was a handy graph back when I was managing the customer-facing web development. Kibana, more sophisticated interface into some of the same data. This is a graph we call Rob's storefront errors because we have this director in the storefront named Rob Klein who just pushes out a lot of broken code and causes a lot of then he looks like that. No, that's not what this is at all. He's a director in that group, and he cares a lot about making sure that Wayfair is running really well all the time. And so we do have these quite handy tools that allow people like him to just put together a bunch of things that are really going to tell them what's broken and what's right. So that's they can call them whatever they want, and then everybody links to them, and that's how we run the business. So not just for the web. Those are the iPads that I was talking about in that other thing. We do use the legacy of SQL Server is not far away, right? So SCOM is a Windows monitoring tool. So this is database health at Wayfair. And now I got a list of all these things. If you want to sort of do this yourself, now I've sort of told you how many people you need to make this happen and what types of technologies cover what we think of as all the bases when you have the type of requirements we have, which are, it's not, we don't have to have the type of uptime of some kinds of companies, but we try to keep the store open as close to all the time as we can. Log stash should be called log router because that's really all it does. It routes our log files and log messages where they should go. Elasticsearch with data on physical machines. We don't, if we'd started Wayfair 10 years later, we probably would have done it on the cloud. We have nothing against the cloud, but we built it up to scale before the cloud was really a thing. And we really have no reason to switch, right? So we use physical machines with SSDs for the hot data. These Elasticsearch is for the emerge, and Kibana are for these kind of emerging operational problems that we have. We have other ways to analyze data that's colder. And there's sort of medium cold Elasticsearch nodes. We use the Tribes product or Tribes open source project, which is associated with Elasticsearch, to have one view based in our Boston data center, but that includes the Elasticsearches that are in Seattle and Ireland, right? So the data from those data centers is flowing into a local Elasticsearch. You have the largest cluster in Boston, but then you've got these kind of thin windows that are behind the scenes querying the Elasticsearches elsewhere. So the developers and everybody else is looking at what's going on can look at one place. They don't have to go to a lot of different consoles, but the back end is distributed, and that works fine. So the tribe and master nodes are just VMs talking to the SAN. We have SQL Server OLAP and Vertica for our big dash system that the conversion chart is in HP Tableau. Graphite with Carbon, sort of, not fancy graphite. That's the file-based storage that Carbon uses on VMs in a SAN. We put all this in, if you want to look way back for months, a lot of this data, or maybe all of it, goes into Hadoop, which is we run on Dell CX8000s and moving to the EMC Isilon thing. We have lots of statisticians. They run R and Excel on desktops, and we have some big RAM machines for them. We run Zabbix with the default MySQL backend, SCOM plus SQL Server. So pretty generic. There's some commercial products in there, but it skews very DIY. All right, so the scale, our Hadoop cluster has about 160 terabytes. Elasticsearch, we keep two weeks of data for WIF, the network sniffer. And we keep 48 hours of everything that goes into Elasticsearch on these hot nodes with 1.5 TB SSDs. 2 months worth, 60 days on cold, which are 10 terabyte spinning disks. Partitions every hour, a few million messages, which is between, depending on the time of day, 5 to 26 gigabytes per hour in Massachusetts. So I don't know, maybe not for the faint of heart, but e-commerce business is pretty good, so can afford enough hardware to run all this. So that the Hadoop cluster is the big data. It's a kind of a joke in the big data industry that big data is for for companies that don't trust their data scientists to be good at statistics, right? So if you just put in all the data, then you don't have to do any stats on it. You can just query it directly. You certainly don't have to sample it because you've just got it all there. We've got plenty of people who are perfectly good at stats and sampling, but not everybody. Stupid people like me can just query the data directly because sampling is hard, and that is going to take us to the next part of the evening. If you have any questions about my talk, let's hold those till the end. You can catch me later. Without further ado, Baron Schwartz.
All right, sampling is hard. And now that I know there are data science people in the room, you probably know way more than I do about sampling. So I'm Baron Schwartz. I'm the founder and CEO of Vivid Cortex. We do database performance monitoring. And I was going to try and invert this logo and then ask you to close and open your eyes so that it would look like it was burned into your retinas. But that's the extent of my advertisement for Vivid Cortex for the evening. I will talk just a bit about what we do to kind of give some context for where this comes from. One of the things that we do is sniff network traffic off the wire on database servers and then reverse engineer the TCP protocol and pull out queries and time them. And so we get a lot of data from that, but we try and gather several different kinds of the data so that we can get a real description of what's going on in the database server. The thing that we're best at, the thing that most of our customers are buying us for, is really this query insight. So there's lots of things that you could do to monitor a database server, the status variables that you get out of it and the logs and all of these kinds of things. But where we really specialize is in the queries. And so that's what we're sniffing off the wire, and that's what we want to get some samples out of. So I'll have some pretty pictures that you can imagine are queries or something else of your choosing. Maybe it's events from a log or something like that. But what I wanted to talk about was how we designed a set of sampling algorithms that met our needs. So we have these queries streaming across the network, and we treat those as events. When we see a query coming into the database server, we note what it was and its time, and when the server responds, we have a timestamp there, and we subtract and get the timing for that. And we accumulate these statistics. For example, the total accumulated time, the frequency of the queries, those kinds of things, and then we sample that once a second. So we have once per second high-resolution metrics of this query stream. Generating metrics about queries is interesting, but we will, I'll show you why we want more information about the queries as well. So this is, for us, this would be a stream of queries coming across. Like time goes left to right, and this is a stream of queries, and we're going to, there are things about them that we can measure, including their time and their latency and those kinds of things. So we generate these metrics about the stream of events, but the metrics are not enough. We really want more. We want to have some of those individual queries that we select out of the stream, instead of just reducing it all to metrics. We want to keep some of those individual queries so that later on, when we say this kind of query looks bad, we actually have some examples of that query to dig into. The exact origin host where it came from, the user, the current database, the exact SQL, that's the really important thing, the explain plan or other execution plan. We support MySQL, MongoDB, Postgres, and Redis at the moment. So we're capturing these individual samples so that when you see something about a type of query that's interesting, you can dig deep into it and have a specific example to look at. So we want to get some of those little circles and keep them. And this doesn't seem like a really hard problem. But we found that for our requirements, it was kind of much more difficult than it looked, because streams of queries really look more like this. So I have 4 colors. I hope this is not bad for people who are colorblind, but I have 4 colors on here, and you'll notice there's also different sizes of circles, and some of them there's a lot of them, and some of them there's not very many, like there's not very many green circles. So query workloads are usually highly diverse, at least hundreds of categories of queries. We categorize queries by taking away the changing parts of them, literals, collapsing white space, things like that, and grouping them together into categories by what remains. And so those would correspond to the colors on this chart, for example. So some of those kinds of categories you'll see occasionally, some of them you'll see constantly. And so now sampling this becomes a little bit more interesting, a little bit harder. And there's also things that might make an individual query really important for some reason. Like the big green circle in there is bigger. Maybe we want to treat that as more important. Like this one's an outlier. We really want to have an outlier example. So this is kind of taking samples from a diverse set of stream of events is what turned out to be a little harder than just picking samples from the stream. So there were a set of goals that we had. We wanted to get enough events that within a reasonable time period you could look and find some examples. So if you've zoomed into like the last hour of the query workload on your server and you see one particular query that's of interest, and you click through to the samples page and it's empty, that's a bummer. You usually want to have a collection of samples there. We want events that are representative of the whole, and not skewed towards some particular, or not too much skewed towards some particular set of the events. We do want a little bit of a skew towards ones that are important for some reason. Maybe they have an error or a warning associated with them. We can see that on the wire as it goes back across the wire. Or maybe it just has a really high latency or something like that. Sometimes, this is the bit of private information about our customer systems that we're looking at, the SQL. It may have personally identifiable information, so we have to put some filters in there to do things like filter out queries that might have, let's say, social security numbers or some of those kinds of things. So we want to avoid sampling those. There's a lot of filters like that. We have some pretty sophisticated kinds of functionality to catch things that people might be really interested in. And we don't want to do something where the high frequency events will get sampled a lot and the low frequency events will get sampled the same proportion and we'll never see any examples of them. But at the same time, we don't want, customers have very different workloads. Some people's database servers have 5 kinds of queries at really high velocity. That's an extreme case. Some people's database servers have literally hundreds of thousands, millions, sometimes tens of millions of different kinds of queries. That's another extreme case. Most customers' databases have several hundred at least different categories of queries. But we don't want any edge cases where we're going to run into we're sampling a lot of stuff and pounding our APIs with the query samples or causing CPU or memory problems in the agents that are running. So we want to achieve generally an overall desired sampling rate. So some of these goals are conflicting with each other. The bias towards important queries is in conflict with rate limiting overall, or rate limiting even those categories of queries. And the rare versus frequent versus overall sampling things are in conflict as well. So it's kind of hard to balance some of those things and then still to get representative kinds of samples that illustrate the general typical as well as atypical queries. So we started out with some things that didn't work very well. And I have a pretty long background in MySQL, and I wrote what's now called Percona Toolkit, which has kind of the definitive log analysis tool, query log analysis tool for MySQL. And the way that we handled this there was when you would aggregate a log of queries for a range of time, we would pick the worst sample during that whole range of time for you to look at. So if you collected an hour of query logs and aggregated them all up, you would see for each category, you would see the one individual query that had run longer than all of the others. Well, this is not very good for if you're trying to find typical queries. So it's like one of the simplest things that you could do because it's really easy. It doesn't take much memory. You just keep a query, and then if you see one with a longer latency, you replace it and keep that one until you see one with a longer latency. So it's not too hard to implement, but you get extremely skewed sampling. You never get any typical queries. Also, that tool was based on aggregating a single chunk of log file, and you would get one sample for your whole chunk of log file. We're collecting these things continuously, and you want to be able to look back at windows in time and see samples of what was going on in the server all along your time scale. And so you can't just, I mean, you have to sample things at some regular repeating time interval. So selecting the worst or selecting the other thing you can do is just select every nth event. That one breaks down really quickly because then you sample at high frequency from high frequency events and very low frequency from low frequency events. So we turned to statistics, and here we started to dive into a little bit of math that later on we realized, oh, we didn't need to do that, but I'll kind of take you down that road. Anyway, so without getting too fancy, basically most systems where events arrive from something like, web traffic or things like that are assumed to follow this distribution called Poisson, and there are particular properties of that, the inter-arrival times and so forth and so on. And one of the cool things about that is if on a relatively short time window it's arriving at a relatively constant average rate, and the inter-arrival times are kind of, they're not completely uniformly spaced. There's like some clustering here and some squishing apart there. And, things are a little bit irregularly spaced. There's a property about that called memory list, and it relates to the exponential distribution. So you can use the exponential distribution to try and select an appropriate probability for sampling every event that you see. You can read on Wikipedia about the exact math of this. But here's a picture of what the exponential distribution does. It's a negative exponent. And as time passes, it approaches and approaches and approaches the probability 1. And so the idea for this is that if you want to either generate or sample things at a regular repeating interval that approximates doesn't approximate it, it is your Poisson distribution, you can use the exponential equation to tell you your desired probability of sampling any individual event. So we kind of went down this path and it was working, but at the rates at which we see events, it was a little bit CPU intensive. And if you zoom in on the very front of this chart, of this function, it actually approximates a straight line. And so what we ended up doing was using a uniform distribution instead of exponential to keep things simple. And so the way to think about this, we actually thought about this. It's kind of subtle, and it still trips me up sometimes. But I thought about it wrong at first, and we implemented it wrong at first, and started way oversampling everything. The way to think about this is that if we want to sample at a particular interval of time, let's say we want one sample every 3,600 seconds every hour. What you do is you measure the last time that you have seen an event, and you remember that. That's just a timestamp. And then when you see an event, you subtract the timestamp, and you go, it's been 2.5 seconds since the previous one that I saw. What's the probability that I should select this one based on it being 2.5 seconds since the last one that I saw? And you can either use the exponential distribution, or as we do, we actually use a uniform distribution where we select a slope as our probability. And when you add these slopes up, measuring from one event to the next, I don't have any scale on this, but let's just say that the slope of that first triangle ends up at a probability of 0.05, and then there's a little bit of time between that and the next one, and the probability of that one is 0.03, and then there's 0.07 for the next one, and eventually all of these probabilities will add up, and you will eventually sample something. And especially if there's a really infrequent query and you want to take samples every hour, if it's been an hour or more since the last sample that you saw, your probability is going to be greater than 1, and you will sample that query. So that's a great simplifying thing for us, and saved us a lot of computation, saved us a lot of complexity, and it becomes difficult when you implement this in a really high frequency system with lots of complex code doing other things. It becomes kind of difficult to understand this and what's happening. So we still had some challenges even with this simplified method of selecting the probability of sampling any individual event that we saw. In the edge cases, well, first of all, we were conscious that there were edge cases, and secondly, we started to see them biting us when we rolled this out. So we rolled it out rather slowly. Our agents run on customers' machines that we have no control over. We have some visibility into them because we've instrumented them pretty well. But it's kind of, I sometimes call it a hostile environment. There are versions of system libraries and things that we don't have any control over, and it's a high performance environment. We're installing an agent onto somebody's database server, or they're installing for us. And we need to make sure that it runs efficiently and correctly and reliably. So we started to see some challenges in particular workloads. One was the really diverse query workload where we have millions of categories of queries. For efficiency reasons, we don't remember everything about these categories of queries over time. We have an LRU, a least recently used list, and after a while, after we haven't seen a query category anymore, we forget about it, just to save memory. Because if we're going to have tens of millions of things in our LRU list, it would start to take a lot of memory. So we drop things off after they've been inactive for a while. Well, that's an efficiency for memory particularly, because we want to have tight bounds on memory. But it also means that we're forgetting the last time that we saw an event in that category. And if we forget, then we think that we've seen, the next time we see one of the events, queries in that category, we think we're seeing it for the first time. And we'll sample it. We'll select that sample. That's one of the heuristics we use. The first time you see a query in a category, you sample it. And then you start the probabilistic sampling. So it turns out that when your LRU list is sufficiently small to save yourself memory, and your diversity of query workload is sufficiently large, you'll LRU things all the time, and you'll way oversample the long, long, long tail. So we started to cause some problems there, mostly problems with our API. So we started to look into our storage for the query samples, and we were like, what? We're storing how many query samples for this customer? And of course, when customers would go and look at their web user interface, they would see very poor response time because they were pulling huge amounts of data from storage. There are other cases where we would undersample things as well. I don't remember the specifics of that off the top of my head, actually. So I've already mentioned a couple of the solutions here. One is using the uniform distribution, but the other thing was finding some cheap and approximate way to remember in a very bounded amount of memory the last time that we have seen, or something approaching the last time that we have seen, a sample for a given category of queries. So statistics came to the rescue again, and this time we weren't really able to simplify it, but it's actually fairly simple in the end anyway. So we were just kind of noodling around about this, and I had read about the count min sketch, never implemented it, never used it, but it was something that had stuck in my mind. I wasn't writing this code, so I said, hey, what about a count min sketch? I mean, it feels like something applicable. Could we do like a last seen timestamp sketch, something approximate and bounded, with some well understood amount of imprecision? And sure enough, it turned out that we could. So I'll explain to you how the last seen sketch works. And after we implemented this, we actually found somewhere in some obscure paper that someone else had implemented this in kind of a similar context to us. So it wasn't completely original. It was sort of like, who were the two people who discovered calculus together? So independently, yeah. So that was kind of the way we felt after that. So the last seen sketch, I'm not going to explain the count min sketch because it might be kind of confusing to think about both of them, but the last seen sketch is an array of arrays of different lengths. And the arrays hold timestamps. And as we see events, we're going to start recording them into these arrays. So the arrays there are many more of them, and they're much longer than this. But this is sort of, this table on the right is kind of a condensed example of how this works for us. So when we see a category of queries, we take a checksum of it, which turns into a number that we can modulo, and we modulo at the length of each of the arrays. And that will be the index in those arrays where it maps to. So it's kind of like a hashing function in some ways. And so our example is that we want to store timestamp 8 for category that hashes to the value 20. So 20 modulo 6 is index 2, and that's the green one up in the top array, in the middle of the top array. And 20 modulo 5 is 0, 20 modulo 4 is 0, so those are the first index in the second and third arrays, and then 20 modulo 3 is also 2. So when we see our query that hashes to the value 20, and we want to store timestamp 8 as the time that we have last seen an event for that, we're going to go to these arrays and these indexes and just store the value 8. And we'll do this for every event that we see. It's pretty cheap. It's just a couple of integer sets, modulos and things like that. And doesn't add noticeably to CPU. In fact, this was a lot cheaper than the LRU that we had been keeping previously, because the LRU actually was a hash table, or included a hash table. So we've stored 8 in 4 places. And in the future, if we wanted to ask where we got that from, we would end up back in those same cells, and we would find the value 8. Now what happens is that since there's different lengths of arrays, these things get staggered, and there's prime numbers and all kinds of other things that come into this. But basically you're going to put these values in predictable yet well-mixed buckets in cells in the arrays. And after you do this, you're going to have some collisions, because some things are going to hash and modulo to the same thing that are not the same value. So when you go and look something up, you won't find the same value in all the same places, because something has come along and collided with you and overwritten part of your values, maybe all of your values, but most often part of your values have been overwritten. So if we want to find the timestamp for the query that hashes to 13, we find the indexes, and here I've highlighted those in yellow. And you go and you look up all the values, and there's a 4, 9, 3, and 9. So if you think of the process of how this one got stored, it must have gotten stored as 3333, and then something came along later and kind of stomped on some of those cells and updated them to other values. And so what we need to do is take the minimum of all of the values that we find, and that, as long as there hasn't been a complete collision where our storage for this value has really been completely wiped out in all of the cells, that will be the right value. So then it becomes a law of large numbers, and how likely it is that you had a complete set of collisions that completely erased your values. And in that regard, the math and the mechanics of this are all the same as the count min sketch, which has been extensively studied, so we didn't need to do all of that. We did a whole bunch of experimenting just to make sure that we were getting the kinds of results that we wanted, and we did end up getting good values for this. So the only thing that we had to do was make our sketch sufficiently large, with enough arrays that are sufficiently large. And ta-da, we have something that can take tens of millions of categories of queries and approximately remember the last time that we saw any event for them. So when we put it all together, we categorize and flag these events. Some of them are called important because they have an error or a really long latency or something like that. We blacklist some of them, so we don't sample them. And then they're eligible for, if they're still eligible for selecting as a sample, then we look in our sketch and ask, when is the last timestamp that we saw an event in this category? How long ago has that been? We just subtract. How long ago has that been? And based on our probability per time, what is the probability that we should select this one? Then we take a random number. If the probability is larger than the random number, we select the event, and we're done. So in the end, This is actually the same bubble chart as before, but I've deleted most of the circles. So in the end, we get something that looks like this, with a small and maybe bias towards important, but otherwise representative sample of the events that we saw in the stream overall. And then we have these rich streams of metrics. And we can put the two of them together and pretty well describe the workload of a server, even if there are millions and tens of millions of categories of things going on in it. So examples of this, and I'll show some examples of biasing towards queries that are particularly interesting because of warnings and errors. So suppose that we're sniffing queries off the wire, and once in a million or once in 100,000 or something like that, we see one with a warning. And this actually happens. We found some bugs in third-party software, for example, where they would have edge cases and try and set a variable to a negative number, and that would come back across the wire with a warning, and we would catch that and then report it, and it would go to the vendor, and they would fix it. And so, this kind of production visibility has real benefits, but it only has benefits when you can actually, if you can see that 1 in 100,000 queries had a warning, but you can't see which ones, it's pretty useless, right? So you have to actually find the examples of the queries that were problematic to sample. So here's one that I forget what this screenshot is over, like the last 3 hours or the last 1 hour or something like that. We had 23 occurrences of warnings, which is 0.001%, which is what, 1 in 10, whatever that is, 1 in 100,000 or something like that. It's pretty infrequent. And when we drill into the samples that we have of that query, we get something that looks like this. And the circles are just a visualization of the samples that we took of that category of queries. And the circles are interactive. You click on them, you can see all the timestamp and latency. And you can also see on the far right, there's I'm not sure if you can really see it, but there's a little box that says warnings 1. That's something we capture out of the network protocol. And then, of course, down below, there's the exec SQL. This one doesn't bother me because this is in our systems and we're creating a table that may exist with a create table if not exists. If the table exists, it comes back with a warning, so it's not a problem for us. A more relevant example for one of our customers, this is MongoDB. We noticed that not only this type of query, but a lot of queries were coming back across the wire with errors. And when we dug into the error, it was, I forget what it's called, it's scan not allowed error in MongoDB when an index is not used and it's going to look at too many documents in a collection. And it turned out the reason that it was doing that was because there was no index on the collection. And they thought there was an index on the collection. But the reason there was no index is because the create index had a typo in it, which was also throwing errors. So they thought they were creating indexes, but they had unindexed collections. So their dashboard in the app, just kind of blew up with errors immediately. They immediately saw this. So what's kind of interesting about this, I think, is that you can have, it's very difficult to catch and log these in an application. With the best of intentions, you will make an if not error do something and forget the else. And then the error never gets logged. It never gets, there's an error that's coming back to the application and nobody finds it, but you'll see it in the network traffic. And so then we can pull these things out and help people actually do better in their databases. So that's all I had. Happy to answer questions with your guidance on what amount of time you want to spend on questions and so forth. I do have my contact information here. And by the way, I need a few more Twitter followers to get me over a threshold. I'm so close.
We can spend, I hesitate to say we can have infinite questions, but we can spend as much time as we pretty much
Okay.
want.
Yeah, I'm happy to answer infinite questions. Okay, great. Yes.
What else makes queries important, and how do you track queries that take too long?
Uh-huh. Yeah, great question. What else makes queries important, and how do we track queries that take too long? Importance can be determined by warnings, errors, latency over a threshold, which we set by default at 1 second. That's configurable. And in the MySQL protocol, there's actually a flag in the network response that says the server This was actually over to the server's slow query threshold. So there's a query was slow flag that comes back through. There's also a couple of other flags. It depends on the specific protocol. MySQL's protocol is pretty rich. There's one that says no good index was used, and there's another one that says no index was used. So we treat those as important, and we will sample those with a higher bias. Other things that might make a query important, we had one customer who I was going through a sales process with them, and I wasn't really listening to tell you the truth at first. I wasn't really hearing what they were saying. We were talking about the normal value that Vivid Cortex would provide and so forth. And then after like the second or third call, I suddenly realized that they were telling us that their real problem was that they had a complicated application with lots of legacy code bases running maybe in some cases on servers that they didn't even know about. And there were tables that were changing that weren't supposed to change. And so I said, we can fix that for you. Let's go build ourselves a little importance flag in our agent that'll take a regular expression or a text substring, and then we will set those as very important and set another parameter, how many of those we want to forcibly sample. So it was something like update the users table or something like that. So we did update.star_user and select the first 100 samples of this. And the next time that they had this, instead of taking downtime to enable full query logs, logging queries for a day, pulling the logs off, grepping through them, et cetera, they were able to, we just configured this and sniffed, and the next day we went back into the dashboard and looked at the samples, and all the samples of the queries that they wanted were right there. So that was pretty cool. So there's a whole bunch of other flexible things that can set a query as being important. And the other question was how do we determine that a query is long? That's just a configurable limit. Yeah.
You said you filter sensitive queries. Do you ignore them or do you anonymize them?
By default, we anonymize queries. Let me scoot back here a little bit. Oh, I actually don't have this in the screenshot. We anonymize the vast majority of data that's coming through about queries. The queries are identified by something that has all the literals stripped out, so there's nothing sensitive in the queries anymore. Select star from user where ID equals 5 just becomes ID equals question mark. So the vast majority of the data just turns into metrics about queries, metrics about these categories of queries, and the metric names don't even include that SQL. They just include a checksum of the SQL. So the only thing that's sensitive that remains is the individual samples, these little circles here that we're taking. And so when somebody is concerned about, we have multiple customers who have patient health information, PCI compliant customers, the like. When somebody's concerned about those things, we'll work with them to identify sets of patterns that we should blacklist for sampling entirely. So we can blacklist, we can whitelist, or we can do this audit flagging. So we usually blacklist things. People will have specific table names, like I don't know what it's called, the payment card table or something like that, and we'll just blacklist all queries against that. Yeah.
Have you guys done sampling of other types of queries, like Solr queries or just database queries?
At the moment, we've only implemented support for MySQL, Postgres, Redis, and MongoDB. And actually, for the longest time, it was just MySQL. We were kind of building the platform and the product around that. And then in the last few months, we've added Postgres, Redis, and Mongo. So we're adding new platforms. We haven't done Solr yet. But actually, somebody just today kind of told me that would be the killer use case for them. So if that includes you too, then we have enough votes to make a quorum. But it is, the way that we capture and time this data and all of the other things, I haven't talked, it's a pretty rich functional product, but the way that all of this stuff ties together around it all applies to this principle of a system that accepts requests, whatever you call them, queries, requests, commands. People have even asked us to build, web or HTTP APIs, those kinds of things. So it could all fit in there. It's just a matter of like which ones we get to first. Someone else was starting to raise their hand. Yeah.
Large quantity data coming back is very slow, and it will take a whole network to slow down the whole system. Actually, I mean everything else coming out is so you sample by the size of the data, payload.
So the payload, for example, the rows that a query might return from.
Multiple result sets could be like 20, 30. Some people write crazy programs, like 10, 20 result sets.
For efficiency, we actually. So the question is, do we sample by payload size? We could. We actually ignore almost all of the data that comes back from the server to the client. It gets really complicated. We don't want to try and reverse engineer, a billion rows. That's reconstructing the protocol, the TCP, and then the application protocol is pretty expensive to do that. So we every protocol that we build a sniffer for, we have to do a whole bunch of engineering to try and pull out the interesting bits and ignore the rest. But I think we could just count bytes for payload.
That would be enough.
Yeah.
Some of data.
Yeah, it's a good idea.
The web page, so you want to cycle the data, but it's for mobile apps.
Yeah, that's true. Yeah, really heavy queries by bytes returned. Yeah. There's something else that we do in order to try and avoid measuring every single dimension about every single category of things and getting this like cross product of combinatorial explosion of bazillions of categories times bazillions of metrics. We have a regression technique. It's basically a simplification and efficiency hack on top of multiple linear regression. So often we will do something like we'll use regression to tie together the likely relationship between lots and lots of categories of queries and a single metric such as bytes sent from the server to the client, and try and figure out, first of all, how statistically solid that correlation is, and secondly, which categories of queries appear to be sending the most data back to the client. But your point is still a good one. Like, this is something that we could do in our agent. I'd put a threshold on that. At first, I thought you were asking about like the size of the sample itself, the payload of the SQL, and we actually have some thresholds on that as well, because if somebody can possibly send a 1 gigabyte query to the server or a 5 gigabyte query to the server, they're going to, and sure enough, some people do. So we have thresholds and like safety breaks on every possible thing that we could think of. Some of which we did not think of first and added after the fact. Should we switch off and ask some questions for Ben? Do you want to do that?
Anybody have any questions for me?
I do.
All right. I will come up here so we can do a joint session.
I was curious whether in one of your later diagrams you have PHP but you don't have ASP anymore. I was curious whether you're still running on Windows, if there's any more ASP, kind of what you're...
We served our last customer-facing ASP request in April of 2013, and we had a party. It took the form of an Irish wake, You know why wakes are called that? The idea is you have a loud enough party that if the person is not really dead, he will wake up from what looks like a sleep. So we wanted to make sure that ASP was really dead. We still do have some internal tools that use it, but it's no longer on the forefront of if there's a fire in one of those. Okay, get to it when we get to it. So yeah, it disappears, at that point.
And are your servers all running on Windows? Are you running PHP on Windows?
No. We're running PHP on Linux, on CentOS 6.3 or 5, 7 soon. So they talk to SQL Server, but they also talk to all those other boxes. My boxes and arrows diagram, which include MySQL, small amount, MongoDB for our flash sale site has some of that. There's a decent amount of Redis and memcached, and a lot of solar, and some other things. And,
Is that another code for solar?
I guess so. Yeah, well, we use, as I mentioned, we used Elasticsearch does that, partition by date thing really well, right? So we have these files that are just globs of hours worth of data coming in all the time, and you can just easily sort of drop off the 2-month-old stuff at the end. That's one of the big use cases for Elasticsearch. For the catalog, where we don't have that kind of partitioning to do, it's a big catalog as its businesses go, but it's not terabytes and terabytes of data. We sold it for that, and so that's Elasticsearch is internal facing, Solar is customer facing, so that would be in the if it's broke, we need to fix it right away. General category about which you are, in a sense, inquiring.
I'm not doing a sales pitch,
Yeah,
standing
yeah.
in front of a room full of people. I would never do that.
It's funny. This is a mixed talk, right? And sometimes I get this question. Why don't you have more people who are like me, who are practitioners at some company, putting in place all these things? Because those kind of war stories about how you put this stuff together can be interesting. And my view of it for the meetup is that whether there's an element of salesmanship or not, there usually is in some sense when people are coming from these product companies where their business is to make something that people are willing to part with money for. And I think these meetups are a chance for people who do that in their working lives to sort of dig in on the technical aspects of it. But because they've had to kind of wrestle with that question in a way that just people who are operating web stores like myself haven't, there's this sort of pressure on them to innovate and really be out front. So if we can get the people like you who have something to sell to talk about the technical parts of it, then it makes for some good talks. I've certainly had good luck with that in general MO. Time I've been doing it.
I have a question. Which one of the web monitoring tools is your favorite and that you rely on the most? Or like it's kind of like your go-to?
Well, I'd say, each one of those little pieces has its role in the composite system. So, it's almost like if you're on a desert island, would you, could you choose one of them? I don't know. I mean, graphite's great for raw counters. Elasticsearch, you can do some counting, but it's really there so that human beings can zero in on things. These other tools have their sort of reasons for being. I don't know. I mean, I guess within the confines of our infrastructure, the Kibana Elasticsearch is probably the single most useful thing for the largest group of people in Wayfair. But that doesn't mean that the handful of people who are using some of these other tools don't absolutely rely on them. If all that started to break and they didn't know it, we wouldn't have a 3-alarm fire pretty quick. So my favorite is sort of different from maybe how important they really are.
Yeah. Got it. Cool.
So with Vivid Cortex, you're making an agent that's running on each machine. So I understand you're using Go or experimenting with that. Like, what was your experience with that?
Yeah, choosing Go, I chose Go for the agents really early on, when it was just me. And so my experience writing Percona Toolkit had informed some of that. I led the consulting team at Percona, and Percona Toolkit used to be called something else. I actually created it before I even joined Percona. But it became really useful for the consultant. We would get emergency calls, and within a few minutes, we would be telling people which SSH key to drop into their server, and we would be SSHing in and trying to fix burning fires. And I had written these tools in Perl that were really helpful. The problem was they had some module dependencies. And so then I started bundling all the modules and concatenating the thing into one big file with modules inline in Perl. And this kind of goes to a natural conclusion that in Perl land doesn't look very pretty. But I needed things that would run and have as few dependencies as possible. And and then I started writing things that were very performance sensitive, and Perl's not really a high performance language. And so by the time I had decided to found Vivid Cortex, I knew that I had years of experience kind of struggling against dependencies and struggling against limitations with concurrent programming, parallel programming, and just high performance computing. And I knew that we were going to be doing some really performance intensive things. So there was a limited list of things that could be statically compiled, it wouldn't have dependencies, and would be high performance. So Java is kind of a natural thing, except that then it requires a JVM. C and C++, you can certainly do it, but I don't think anybody talks in glowing terms about how easy it is to write correct concurrent programs in C and C++. And then Go was sort of nascent. It wasn't really bleeding edge. I'd been keeping my eyes on it for a year or 2 years or something like that, but had never tried it. So I just started experimenting with it, testing how good the driver support was for MySQL, a few things like that. Had a good experience with it. It does make concurrent programming extremely simple. It's highly readable. It statically compiles. It's got a lot of nice properties. There's very little that I don't like about Go. So it's been great. And then our whole back end is built on Go as well. All of our APIs, both internal and external, all of our worker programs, whether they're doing little things that I previously would have written in a bash script or something, or whether they're doing really heavy lifting, it's all, it's go, 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 go. It's been great for us. It's also really easy to, it compiles fast, which matters a lot when you're trying to deploy things quickly and running them through continuous integration. So it's super nice to be able to push a commit. We use GitHub, and we use CircleCI integrated with that. And when CircleCI gets a webhook call that somebody has pushed some code to GitHub, it just runs all of our tests. And having a 30-second feedback loop is it's a beautiful thing. And most of that 30-second time is it's like kind of setting up the test fixture, not running the tests. We even use Go. We moved away from a static site generator written in Ruby, Jekyll, to a Go-based one for our website and our support documentation and all of that kind of stuff. Because when you're deploying the website, the difference between an 8-minute website build and a 15-second website build is a huge amount of productivity. And this all, we've given some talks. I think you can find videos on the web about how we've integrated this all in with Jenkins and CircleCI and automatic deployment and our chat system. And, so Go is a key part of that. Like having things that are easy to just build and then ship around and not worry about dependencies going with them, or configuration management and all that kind of stuff. I do promote Go pretty highly. Big believers in it. Yes?
So you mentioned your code is, because you have a code for different kind of type of databases, and when you deploy them, are they deployed as using like a Docker framework, or as like a virtual machine framework, or how do you actually deploy this to the client machines?
For the client machines, there's a set of agent programs, and everything that we rely on, we've had to write ourselves, essentially. There's a supervisor agent that basically takes the place of init. Once it's started, it daemonizes itself, and we had to, Go is not written to be daemonizable, so we had to do some stuff to make that possible. And then it starts the other agents. It inspects the environment, it says, I see a Redis and a MySQL, talks to our APIs, says, what should I run here? The API says, well, you should run Redis agents and MySQL agents, and here's where you download them. And it downloads them and runs them, reconfigures them. We have the ability to do things like pull log files, and then to get to your question, we have the ability to download and upgrade or downgrade newer or older versions. So when we release a new version of our agents, we push the code. This one's not automatically deployed. Some things like our website are automatically deployed, but this code is not automatically deployed. It goes through a build and review process. Once it's blessed, then we build the agents and we push them to the download servers. And then there's a separate chat command that we use in we have a chatbot listening in our chat channel for things like /deploy this and that. So we say /deploy, actually this one is /release. /release agents to, and then you can say, you know, one customer, one environment at a customer. There's this notion of environments like production and staging and stuff. All of them. So we'll release to ourselves first, we'll release to one customer first, and then watch for a while, wait for it to get upgraded. That only takes a second, but wait for the metrics to start coming back and see if there's like before or after any kind of metrics, performance metrics to be concerned about. There's CPU and memory and all that kind of stuff, metrics for all of our agents. And then release broadly to everybody. So the agents download and upgrade themselves.
So you basically run as native programs in the client systems, just you know, any kind of executables or events or whatever.
I didn't quite hear some of that. Could you say again?
Oh, I said that you basically run your agents as native programs in the client environment.
Yes.
It was not in a contained environment sort of thing.
Right, yes. Our agents are running natively as executables in the client's environment, yeah. And so they have to run with root privileges. You know, they have to do that to sniff the network traffic. But that's also how they can, you know, upgrade themselves.
That's true, yeah.
Yeah.
Is this something that you, well, it's going to be limited cases where you can do it, but do you think this is something that you would launch as like a network appliance at some point that would like sit in between things, or is this kind of the better?
So a network appliance, you know, people have suggested that we would could build a network appliance that would, instead of being installed on the customer's machines, we would use one of the various methods to siphon the traffic off from you know, a router or a switch, so that we have all of the burden on this appliance instead of running agents on the customer servers at all. So we thought about doing that, but it has never actually gotten to that point. You know, for whatever reason,
Right.
Nobody's ever asked us to do it, but it's theoretically possible. There's a whole bunch of stuff that's kind of theoretically possible that we made sure we didn't preclude in our architecture. Like instead of running clients on the database servers, it's also theoretically possible for us to run them on the client machines, like the app servers, and sniff the outbound traffic and then collate that all together. Possible, but we haven't built it yet. You know, we've just kind of got the open capability if we want to in the future, which I think we will, because one of the interesting trends is that a lot of new database deployments are database as a service. You know, whether it's Redshift or just Amazon RDS. So for cases like RDS, if the server has performance views in it that expose query information, we can use those. But there are lots of kinds of databases, including like Redis, that has no such. So we'd have to sniff the outbound traffic to get query information.
Or for example, if you had a database living on an operating system like Windows that you didn't support, but the clients were not something that you did.
Funny you should mention that, because we're porting our agents to Windows as we speak.
All right, should we call it? We can certainly hang out and talk more casually, but thanks for coming, and thanks so
thank
much
you.
to Baron Schwartz for coming.